Hey, what's up, YouTube? How's it going? We should be live now. Yeah, okay, and I see that the thing is correctly set up. There's so many pitfalls, so many places where you can really mess up while trying to go live. Cool. Today should be a really fun stream. I'm excited. I hope you are as well. I had fun making this thumbnail. I don't like making thumbnails in general. I just think it's such a goddamn waste of time, as is most of YouTube, quote unquote. But in particular, I'm trying to streamline thumbnails as much as possible. I'm going to rant about a lot of non-math things at times, and I hope you all are here for it. I hope it's entertaining. Let me know in the comments if you're not at all interested and you wish that I just jumped right into the math. But anyways, yeah, so this thumbnail today, I don't think I can show it on screen quickly, but today's going to be fun. I do have physical copies of Strang, physical copy of Shilov, and my copy of Norris is currently in the mail. And so what is Norris? This is the first time I've ever mentioned Norris. It's a new textbook just called Markov chains, I believe. And a viewer, and it's a stretch to call this person a friend. We've only met like a couple of times, but somebody I know has recommended this book by Norris in order for me to learn Markov chains. So for a little bit of background context, first off, hello, if this is your first time, my name is Joan. I studied math like 15 years ago, and then promptly forgot everything, worked in Silicon Valley, worked as an iOS engineer, and now I'm trying to relearn math because it's freaking beautiful, and I just want to build up math as a hobby for myself. So I'm no longer interested in going into a research career and going into academia and whatnot. Instead, now I just want to rebuild math as a hobby because it's beautiful and it's fun. It doesn't matter if ChatGPT gets better at it than us. It's just like chess. Like, humans are still going to play chess. Anyway, so there's a little rant. So a while ago, while I did study pure math, ages ago, I did work as a TA, quote unquote a TA. I was a homework grader, and I graded homework for a linear algebra class for 2 semesters while I was an undergrad, which I think I'm proud of that as an accomplishment. Just, getting paid to grade some homework for a college class, like that's pretty cool. I'm proud of that. And I remember that professor, who was an amazing professor, he taught matrix multiplication motivated by Markov chains. And when I took linear algebra, I had never seen Markov chains. My class was just a little bit more pure, quote unquote, in a lot of ways, but then also applied in others. Anyways, I didn't see too many applications of linear algebra in my class. Whereas this professor did a great job blending theory and the pure side of the pure mathematics of linear algebra with the applications, which nowadays that's what I'm interested in. I do want to refresh my theoretical knowledge and my proof-based skills, but this time around I'm really super interested in applications. Like, what can this abstract stuff be used for? And some of it can be used for other math. And I know that I've learned some of that in the past. I've seen how math can be applied to other math. And that's an awesome, valid application in itself. But some of this stuff is very, very useful in the real world, quote unquote. And right now, the latest, hottest, most fashionable mathematics and most fashionable application is ChatGPT. So we can all use linear algebra to build Skynet or the Star Trek utopian future universe. We'll see how it turns out. But in either case, the mathematics is key. Like, all of AI is built on mathematics. And I've always said that linear algebra is, to me, the perfect math because it is incredibly beautiful and it's an introduction to proof-based mathematics for a lot of people. But then it's also unbelievably useful to the real world. So, I remember this professor used Markov chains to show, to motivate matrix multiplication. Today, I want to introduce Markov chains, and I've hinted at it in the last couple of videos. And today, I want to write down the formal definition of Markov chains according to a few different sources. We've been working from this book and this book primarily. Mostly out of this one so far, just because I think it's beautiful. It's really lovely. But that's my bias showing. This is a very pure math book. This one, more applied, more introductory, linear algebra. And then a person I know, has recommended Norris as the book I want to go to, like for a real treatment on Markov chains. So my copy's in the mail, but I found a PDF online. I highly recommend buying these books for yourself if you can. And if you can't, guess what? You can find the PDFs online. Like, that's not a secret, right? But it is so nice to flip through these things, and just like, it's so inspiring. Especially these Dover books. This was like $10, I think. If it inspires you to flip through it physically more often and you open it more often because it's sitting here on your desk, like, how quickly does that save you $10 in time? Like, how much do you value your time? Do you value your time at least at a minimum wage? At $15 an hour or $10 an hour or whatever it is in your state or place? Like, if it makes you a little bit more efficient or it inspires you to practice math a little bit more, how long does it take to save $10 or generate $10 of happiness for you? Like, it's worth it. Buy these books. But if you can't, again, you can find them online. I'm not going to give you a link, but you can find them. Cool. So we're going to write down the definition from Strang. We're going to write down the definition from Shilov. We're going to write down the definition from Norris. I peeked at this yesterday. We're also going to write down the definition from another one that I found called like Levin something. There are three people. Levin, Perez, and Wilmer. Levin, Perez, and Wilmer. I have a bad habit of always just listing the first author's name, so I'll often just say Levin. But especially with this book, I'm tempted to say that's a bad idea, and I might start calling it LPW or something, LPW. Because I see that those names are alphabetized. LPW, that's, PW, yeah, those are alphabetized. Which is my favorite trick in software. When you want to claim that that the order is not important, alphabetization is not perfect, but it's pretty close. It's pretty good. It's a hint that, like, maybe this order doesn't matter. Maybe they all contributed equally to this book. So this is the first one where I'm just like, ooh, I might call that LPW. And I love that, if that's the reason that the names are listed in that order. Somebody tag them in the comment section, and let's hear it, from the authors themselves. Good moment to just say like and subscribe and leave a comment if you find this content interesting. If you want to see more math, less math, more life updates, and me just yapping and chatting. This is a brand new channel, and I'm very excited with the momentum we've built so far. So let me know in the comment section what you like. And let's get to it. So, oh yes, one last final resource is also going to be ChatGPT, because it's scary good. It's scary good, and let's see how it does. Let's compare contrast definitions according to all these folks. Cool. All right. I hope you have fun. I'm going to have fun. I've got 50 minutes left in me before I have to go somewhere. Okay. Cool. We've got somebody watching on the live stream. Hello. How's it going? Say hi. Let me know what kind of math you're studying and if you enjoy this content. Oh, I've got a brand new scene. Here's this new scene. So let me know what you think of this, by the way. New scene. I'm smaller in the corner. I figure like right above me, I could put chat there if chat is getting chatty. But otherwise, I think that this is a way to just like really highlight the math way more. Like we got the iPad way more full screen. Okay, so my gimmick is that we are solving every linear algebra exercise. And of course that's ridiculous, but we're going to do it slowly but surely, or we will die trying. Strang 6.1, yesterday I did exercise 1. A couple days ago, I unlisted the stream, but I just literally wrote out the outline of what Strang's book looks like. Strang 2, Strang 3, solving linear equations, the 4 fundamental subspaces, orthogonality, determinants, singular value decomposition. So I'm going to do this. Yoink, there's an arrow here. So chapter 6 is then eigenvalues and eigenvectors. And I think a lot of books use Markov. Markov chains as a motivation for eigenvalues and eigenvectors. Not just matrix multiplication, but you can come back to it to understand this concept. And so we've done one exercise so far. I don't know if we'll get to another exercise today, but we will at least be, what am I looking for? The word. We're going to mostly be talking theory today and writing down definitions, I think. Okay, and then the one thing that I need to update here is, so string A10 has a bunch of applications, or not applications, exercises. And then one of these appendices is on Markov chains. So let's find that. Where is it? Where is it? Markov matrices, A8. So string. What we're going to do is we're going to create a new page after this one, if I can remember where that is. Here, add page. Okay. Let's use blue again for whatever reason. String A8 Markov. I said blue, but the underline will be blue. Markov matrices. Ooh, and Peron Frobenius. What the heck is that? Peron Frobenius. Okay, cool. So, in a sense, this entire channel is a reaction stream, in a sense. We're reacting to math books because we're nerds. So I want to talk a little bit about, and the only exercise from this section is going to be exercise 0, which means take notes on this thing. So we'll take notes on Appendix A8, but we should also take some notes from Section 6.1, because in the text, Strang does roughly define Markov matrices. So, but like very briefly. So I think that it's most honest, or the true presentation is going to be showing his definition from the text, from the eigenvalues and eigenvectors section, and then write down the definition from the appendix, where he has more flavor. Okay, I could be wrong. Maybe it was in the... Oh, yeah. Here it is. Okay, on page 219, he has a brief description. Okay, so let's get a new page. I have no idea what day it is. Day 13 or something. Day 13. Relearning. Linear algebra. The Math Hobbyist.com. I am available for tutoring. If anybody wants a private tutor in math, classical guitar, or programming, I'm quite good at all three of those. With that out of the way, let's go ahead and write down Strang. How do I want to do this? Definition. Strang number 1, page 219, maybe. I'm doing that because there's 2 places in the book where he defines these things. So, he says this particular A is called a Markov matrix. Its largest eigenvalue is lambda equals 1. Its eigenvector x1 equals 0.6, 0.4 is the steady state, which all columns of a to the k will approach. See Appendix 8. A giant Markov matrix is the key to Google's super fast web search, which is a great detail that I'm glad that he included in this book. I've heard of this before. Google web search, it's like in particular the algorithm PageRank, which is the algorithm that underlies all of Google and orders the links, the 10 blue links that you see on the first page. That is a Markov matrix. It's a Markov system. So we'll learn about that someday. But anyways, what I'm trying to get at here is that this definition is not very precise. Because like if you just jump to the bolded text that says, this particular A is called a Markov matrix. Its largest eigenvalue is lambda equals 1, ... some other stuff. That's not a definition, sir. Like, I'm very confused just jumping to that. I'm very confused at where the actual definition is. But later, so let's try to do this fairly honestly. What he does is he says A, where is A? First column. It's all under an example, isn't it? Or is it? Where is it? Okay. Here we go. I found it. Okay, yeah, this is all under example 1. Oh, and then there's example 2. A projection matrix. Okay, I'm super confused. So this is hardly a definition. This is more like an example of a Markov matrix. And that's fine. So he says, example 1. And again, this is all in the section introducing eigenvalues. Ax equals lambda x. Example 1, he says the key numbers in determinant a minus lambda I are 0.8 plus 0.7 equals 1.5 on the diagonal and some blah, 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 blah. Something or other. So what he has is a equals, he gives this example, 0.2, 0.7, and he shows in the text that the determinant of 0.8 minus lambda, 0.3, 0.2, and 0.7 minus lambda, that this equals lambda squared plus minus 3/2 lambda plus 1/2. And then that factors as lambda minus 1 times lambda minus 1/2. Let's use colors because colors look nicer, right? Okay, so this means that there are two eigenvalues. Lambda 1 equals 1 and lambda 2 equals 1/2. The fact that you can create this characteristic polynomial, which is a term for this, comes from the fact that we are solving this equation, ax equals lambda x. We're finding vectors that are just a multiple of the original vector. How well is all this showing up? Decently well, right? Yeah, you're getting the full iPad. So if ax equals lambda x, then you can subtract lambda x from both sides, right? Ax minus lambda x equals 0. And if you do that, then you can factor this way because vector spaces have this right distributive property, right? And then if you have this, then if that equals 0, then the determinant of the left-hand side of this matrix, A minus lambda I, is going to equal 0. So that's why we're always doing determinant of A minus lambda I. So I is the identity matrix with 1s on the diagonal and 0s everywhere else. So that's the same as saying that for this matrix, we calculate this determinant where you subtract a lambda across the diagonal. Okay, cool. So, and then he gives he gives a little bit of exposition, let's say, where he says, a bunch of things. Yeah, well, he says A minus I, and this corresponds to the first eigenvalue, 1. So if lambda is 1, we're solving A minus 1x, right? A minus I times the first eigenvector equals 0 is ax1 equals x1. That first eigenvector is x1 equals 0.6, 0.4. Luna! I have a cat and she's very annoying sometimes. Luna! So he finds that, and then he finds lambda 2 equals, for the second eigenvalue, which again we found was going to be 1/2 through this characteristic polynomial. Through this one, we solve the equation a minus 1/2 I times the second eigenvector equals 0. Therefore, ax2 equals 1/2 x2. And then he doesn't show the details on this, but you can solve that x2 then is 1 minus 1. That's cool because I'm trying to figure out where he shows how to calculate an eigenvector. But what I'm getting at here is he defines Markov matrix in the text by showing that there's a bunch of words, and then he shows what happens when we keep raising this matrix to higher powers. He shows that all right. He says the first columns, of course he writes out these words, I'm abbreviating. The first columns of a squared, a cubed are 0.8, 0.2, 0.7, 0.3, and 0.65, 0.35. And then he says approaching 0.6, 0.4. Okay? So there's like some motivation. We have some kind of matrix where if you keep raising it to higher powers, the numbers are converging to 0.6, 0.4. And then he has a little bit more text, and then he says column 1 of a to the 100, he has all this boxed and says a 99, 0.8, 0.2 is really x1 plus 0.2 times 1/2 to the 99 x2, which is 0.64 or 0.6.4 plus very small vector. And then all of this is boxed. And he gives us the equation number 3. And he says, this is the first column of A100. We left out some other stuff. Okay, yeah. ... There's some words. And then he says this part that's important. The eigenvector x1 is a quote-unquote steady state that doesn't change because it has lambda 1 equal 1. The eigenvector x2, oh, my cat is freaking out because it's breakfast time. Let's let her have some breakfast. Okay, do not undo. Luna. Okay, all right. How's it going, everybody? I hope somebody's out there. Let me know if the audio is working, because sometimes I hit some really major technical difficulties and I don't even have audio. Okay, the eigenvector x2 is a quote-unquote decaying mode that virtually disappears because lambda 2 equals 0.5. The higher the power of A, the more closely its columns approach the steady state. Then, in the next paragraph, immediately after, we haven't used purple yet. Why don't we use purple? He says, this particular A is called a Markov matrix. Okay, sir. Thank you very much. I'm still confused, as you might be as well. I don't know. He says its largest eigenvalue is lambda equals 1. Its eigenvector x1 equals 0.6, 0.4 is the steady state. Which all columns of a to the k will approach. And then in italics he says, see Appendix 8. And he says, a giant Markov matrix is the key to Google's superfast web search. I'm just going to abbreviate that as Google. Okay. Okay. Thank you, sir. I know that you are the greatest linear algebra educator ever, but I'm a little bit confused. I'm not going to lie. But that's because I'm skimming around. I'm not reading this super carefully, probably. But I'm also used to a different type of mathematics that presents definitions, theorems in a much more dry way that doesn't box specific examples quite as much, for better or worse. For better or worse, literally. Then I will just say that next he gives example 2, which is about a projection matrix. He has this boxed projection matrix P equals 0.5, 0.5, 0.5, 0.5, has eigenvalues lambda equal 1 and lambda equals 0. And he has this box. There's a little bit of note about the two eigenvectors, x1 and x2. he writes what those are, and then he gives these 3 bulleted items. So this is what my eye was drawn to. And this might serve a little bit better as a definition. But he says, I guess he's saying these are 3 facts about the matrix P, but he has this bolded: Markov matrix, each column of P adds to 1. Then lambda equal 1 is an eigenvalue. Still confused. I'll mention that in a second. Now, this isn't necessary for Markov chains, but or Markov matrices, but I will just go ahead and singular. P is a singular matrix. Lambda equals 0 is an eigenvalue. And then finally, he writes this for completeness. P equal P transpose is a symmetric matrix. Perpendicular eigenvectors (1, 1) and 1, -1. That's not even a complete sentence. Like, what? So I guess he's saying a symmetric... I don't even know. I don't even follow. But I am, again, just skimming around, and I'm not carefully, slowly reading this book. I'm not following a course with lecture notes from a professor. So I'm a little bit confused. But what I'm seeing is here, Markov matrix. Each column of P adds to 1. Then lambda equal 1 is an eigenvalue. He's got that there. And then before, in the prior example, example 1, he says this example is called a Markov matrix. Its largest eigenvalue is lambda equal 1. Now, where I'm confused is, where is the definition here? Where precisely is the definition of Markov matrix? Is this a fact about Markov matrices? Or a result? Like, which is it? I actually, right now, don't know. In other words, every matrix with lambda equal 1, like one of the eigenvalues being 1, is every matrix with lambda equal 1 being one of the eigenvalues a Markov matrix? I don't think so. That's my guess, but I don't know. I am learning this for the first time alongside with you all. So, but I mean, that's all that is stated here. This particular A is called a Markov matrix. The first time Strang uses Markov matrix is the only thing that he says is then its largest eigenvalue is lambda equal 1. Is that the definition? Or is that a result? Because the way he says it later on in this one sounds more like this is the definition. Like, each column of P adds to 1, then lambda equal 1 is an eigenvalue. This feels more like what I remember. what I remember was more this fact. Each column of a matrix adds to one. I think that this is a logical, I shouldn't use A, because A I've been using for matrices everywhere. We're going to run out of time. My God. Okay. Well, there's Strang's first definition. Appendix 8. Let's get to Appendix 8. Let's move on. Because he does say, see Appendix 8. Yep. All right. Strang. Definition according to Strang in Appendix 8 gives a much more clear definition. He says, this appendix is about positive matrices, all entries greater than 0, and non-negative why didn't you just say this appendix is about non-negative matrices? Because every positive matrix is a non-negative matrix, right? Like, why did you repeat that? Oh well. Then he says this, which I find very clear and nice. Markov matrices M are important examples when why don't we use a completely different color just for fun? When every column of M adds to 1. Then he says this nice, helpful thing, which is not necessary for the definition, but it's helpful. Positive numbers adding to 1 makes you think of probabilities. Okay, great, done. We're done here. We can move on, because this is a nice definition. Apparently, a Markov matrix is a non-negative matrix where every column adds to 1. Cool. Okay, and then he gives a couple of examples. Great, let's move on. So there are a couple of examples and definitions from Strang, the most famous, most beloved lecture and book in Introduction to Linear Algebra. And I don't mean to be snarky and throwing shade of any kind to Strang, because I am really genuinely enjoying this book. Especially the exercises are fantastic. But it was not written for mathematicians. And I don't know if it's the best book to learn from for people who want to do serious, hardcore STEM math. Like, if you want to get into AI, if you want to get into AI, nowadays you have to have a very strong linear algebra background. That's just a fact. I don't know if this is the best first book. I don't know. I'm jumping around and learning it for the first time, but I really, really like the exercises. So I want to say yes. I want to say the answer is yes. This is a great book to get for your first linear algebra because of the wonderful exercises and the lecture videos that have been recorded. I keep seeing online time and time again in every discussion, people say that the lectures are fabulous and just like really excellent. I haven't watched them. Sorry. You know, this is my this is my third time through with linear algebra, so I'm going to do better by just jumping right to the exercises personally. All right, take two. Let's get another definition. Definition, according to Shilov. All right, so again, this is more of a pure mathematics book, but usually these books will give you some of these definitions. I mean, there is a lot of beautiful theory, as I understand it, of Markov theory. I mean, like that other book, that Norris book that I did peek at. Whew, yeah, there's a lot of theory there. Spoilers. Okay, just joking.
Sorry, there was a problem with the
literally
app.
does not even define Markov matrices. Like, Shilov, Markov matrices are too much of an applied mathematics for this guy. This guy is hardcore. Even though Section 1 is determinants. Exercise 1, the entire first section is all hardcore determinant problems. And there are some calculation problems. It's not just theorem proof. There are calculations. But this guy did not even include one of the most useful reasons to learn determinants. Like, this is, like, it's just hilarious to me. I love it. So, not even defined. Yeah, I'm kind of acting right now because I did look through the book yesterday. It's not in the it's not in the index, and when I skimmed the text, I couldn't find it anywhere. So, yeah, that's just, I love it. I find that hilarious. Axler, I forget, but I think, if I remember correctly, Axler is also of the same camp. I believe that this dude also I think that he doesn't define Markov matrices. So, that's cool. That's really cool. These two books from Shilov and Axler are really meant for linear algebra for mathematicians, or a second course in linear algebra, which often will have fewer applications than a first course. It's like, these are theoretical linear algebra books. So that's cool. All right, now let's get, I don't know if I'm going to get to, what's it called, Levin? I would love to, but I think we're going to run out of time. I want to at least write down Markov chains from Norris and from ChatGPT. So, oops. I just realized I don't have my Norris on this computer. I have it on the other computer. Oh, here it is. Okay. I guess I do have it. Thanks, iCloud. Okay. I like Norris's introduction quite a bit. It's quite nice. Because he has a lot of examples. But the definition itself is hardcore, I think. Oh my god. Okay. This is going to be a lot of writing, y'all. But we can do it. I don't know what color his book looks like. I think it's a darker blue. So, definition, according to Norris. That's not the most readable color, so I'm going to use a cyan. He says, this is in section 1.1, titled Discrete Time Markov Chains. So this is in a sense, literally the first sentence of this book. Well, okay, there's the intro paragraph. He says, "This chapter is the foundation for all that follows. Discrete time Markov chains are defined and their behavior is investigated. For better orientation, we now list the key theorems. These are theorems 1.3.2 and 1.3.5 on hitting times. Theorem 1.4.2 on the strong Markov property. Strong Markov property. Theorem 1.5.3, characterizing recurrence and transience. Theorem 1.7.7 on invariant distributions and positive recurrence. Theorem 1.8.3 on convergence to equilibrium. Theorem 1.9.3 on reversibility. Theorem whatever on long-run averages. Once you understand these, you will understand the basic theory. Part of that understanding will come from familiarity with examples, so a large number are worked out in the text. Exercises at the end of each section are an important part of the exposition." I love it. I don't think I've seen this before. He literally just says, here's the outline. These are the most important theorems that you need to learn, and here are the short names of them. There's a theorem about hitting times. There's a theorem about the strong Markov property. There's a theorem about reversibility, whatever. I think that's really cool. I haven't seen that in a book before, and I like it. Really like it. But yeah, so he says, section 1.1, definition and basic properties. Let I be a countable set. Okay, so we're already talking about infinity in sentence 1. Each element I in I is called a state, italicized, and I is called the state space. We say that lambda equal lambda I such that I is an element of the set I is a measure on I if 0 is less than or equal to lambda I less than infinity for all elements in the set I. If, in addition, the total mass, we should use different colors, state space, measure, total mass, summation, if the summation of all of those lambda I equals 1, then we call lambda a distribution. Okay. I am completely lost at this point. I never took a probability course in college, and I think we're talking about probability here. I think we are literally starting to talk theoretical probability, and yep, it looks like we are. We work throughout with a probability space. What is this thing? Omega? Curly F and blackboard P. We work throughout with a probability space, which is this triple, and I don't even know what those symbols are. Recall that a random... Is my iPad still working? Okay, good. I think it is. Recall that a random... I'm sorry about my Roomba. If I wasn't lazy, I would turn it off. Let's see. Maybe I can do it quick. Be quiet, Roomba. Don't you know I'm trying to do mathematics on the internet right now? Recall that a random variable, x, with values in I is a function x from omega to I. Suppose we set lambda I, probability thing, x equal I, probability thing, I think that this is lowercase omega, such that x lowercase omega equals I. What the fuck is happening here? Like, I literally am just completely lost. Then lambda defines a distribution. The distribution of x. Okay, this is why I did not go to grad school. We think of x as modeling a random state which takes the value I with probability lambda I. There's a brief review of some facts about countable sets and probability spaces in Chapter 6. Okay, we're running out of time. Next paragraph. We say that a matrix P is stochastic if every row Pij such that j is in I is a distribution. Okay, so here I'm pretty sure we're getting to something that we saw in the prior book. If every row is a distribution, that sounds a lot like what he's saying, what Strang said about every column adding to 1. So we're getting somewhere. And then he says there's a one-to-one correspondence between the stochastic matrices P and the sort of diagrams described in the introduction. Here are 2 examples. I'll skip that part. We shall now formalize the rules for a Markov chain by a definition in terms of the corresponding matrix P. Okay, so I'm going to say ... We say that xn, such that n is greater than or equal to 0, is a Markov chain. Is a Markov chain with initial distribution lambda and transition matrix P if 1, x naught has distribution lambda. 2, for n greater than or equal to 0, conditional on xn equals I, xn plus 1 has distribution pij and is independent of x naught to xn minus 1. Okay. I gotta go -1 minutes ago. But we're so close. More explicitly, these conditions state that for n greater than or equal to 0, something or other, 1 and 2, fancy P, x naught equals I naught equals lambda I naught. Fancy P, xn plus 1 equals I n plus 1, such that given or something, I don't know what that bar means here. Then he says, we say that xn, n greater than or equal to 0, is Markov lambda p for short. Okay, I think we're done. That is the definition of Markov according to Norris, and I am so confused. I gotta go. I hope you enjoyed this. Thank you for watching. I'm pretty sure columns add to 1 is good enough, and I'm pretty sure that that's what ChatGPT says. Columns or rows, Norris uses rows, but they're interchangeable as long as you do the same thing everywhere. As long as the columns add to 1, then you get a Markov matrix, and you can solve all sorts of really cool problems with that. Someday we will understand everything I just wrote down, but right now we're just getting some muscle memory practice in. I hope you enjoyed this. Thank you for watching. My name is John, and I hope you have a beautiful day. Thank you. Bye. Like and subscribe, all that good stuff.